and start this. Okay, for those of you who have made it this far, congratulations for your perseverance. We're in week 3 of Intro to Biostatistics, and I'm about to feed you some statistics with a fire hose, so it's going to feel like a lot, but please make sure you continue to ask questions. I think we've had some great conversation about the topics this year compared to years past. It has kind of slowed us down in terms of how far we've gotten along in the material, but I want to make sure that we cover the minimum at least for what's commonly being applied in biomedical applications. Today we're going to focus on how we use statistics to compare groups. We're going to look at the t-test specifically, some chi-square tests for categorical data, and then we're going to begin those with looking at 2 groups, and then we're going to extend that out to more than 2 groups, touching on the analysis of variance, the simplest of the ANOVA models, and time permitting we'll get to survival analysis at the end, with the idea that hopefully next week we'll be able to get to regression methods. So we'll look at linear regression, logistic regression, probably some regression models for survival analysis applications, and talk briefly about powering and sample size estimation. So it's a very ambitious set of goals, but I think that we can get through the majority of it. But I don't want to discourage you all from asking questions if you have any. So let's just dive right into one of the biggest questions that I usually get is which test is appropriate for the kind of data that I either have in hand or that I'm going to have when I'm done with my experiment. And so the things that you have to think about in the context of developing your statistical analysis plan, how you're going to analyze your data, can really fall into 4 questions. I mean, this is a simplification, obviously, but if you focus on these, then you should be able to at least narrow it down to a group of methods that could potentially be appropriate depending on how your data end up looking. I always start with what the research question is. That's fundamental because that really drives everything. It drives the design of the study, how you're measuring and collecting data, and also how you analyze that data. So make sure you have that research question in the form, if you're doing tests, in the form of testable hypotheses. Of course, that directly informs the kind of outcomes you're going to measure. So you're generally, especially when you're comparing groups, you have a set of independent and dependent variables. So we're going to use this terminology throughout the rest of the course. Independent variables are just your predictor variables. They're the things that you either think cause the outcome or predict the outcome. They might be prognostic factors. They might be the treatment assignment, the actual treatment received, the exposure, some demographic factors, those kinds of things. We generally denote those in statistics with like an X, and meaning in terms of a model it would be the independent or predictor variable. Then you have outcomes. Outcomes usually measure the patient's response to treatment, the progression or resolution of their disease, those kinds of things. So the dependent variables in the model are the things that are kind of the effect that we're measuring. And then you have to also ask yourself, once you've narrowed down the things that you're measuring that will allow you to answer your research question, what information is contained in those data points? So for instance, I did not cover this year like I do in the past, concepts like levels of measurement, which is really fundamental to understanding which test you're going to use. But I would encourage you to write that term down, levels of measurement. Go to Google, and there's a Wikipedia page that will explain it in 3 minutes just as easily as I could. So levels of measurement just indicate what information is contained in a data point and what information is not contained in a data point. And so they inform what's appropriate when you do an analysis. For instance, an outcome or an independent variable like a patient's sex. When doing analysis, it has very different information in it than their age even, right? Because when we look at a variable like sex, all it's doing is classifying individuals into groups, distinct groups. Whereas age, it's still classifying individuals into groups, but those groups are much more well defined, and differences between groups are quantifiable. So if I am 35 years old, then someone who is 70 years old is 2 times as old as I am. Does that make sense? But whenever I do a comparison of a male versus a female, there's no quantifiable difference there. So again, it just has to do with what kinds of information is contained in the data. We generally have 4 classifications of variables in terms of the level of measurement or the level of information that they have. Nominal is the least informative because all it does is classify. Sex, zip code, those kinds of things. They're just classification variables. Ordinal takes it one step up, and in addition to the classification, you also have some inherent ordering of the classes. So I like to use the example of sports rankings. So when KU is first in the nation, and let's say, I don't know, Duke is second, and North Carolina is third, does that necessarily mean anything other than people think KU is the better team than the other two? Another thing that we could compare this ordinal variable to in terms of quantifiable information, the second-ranked team, the difference between the third-ranked team and the second-ranked team is not necessarily the same difference as between the second and the first. Even though they're 1 unit apart, the first and second could be very similar, and the third could be way down below. So when you have that kind of classification where there's ordering, but the differences between the classes is not exactly the same as you go from 1 to 2, 2 to 3, and so forth, you need to make sure you're not trying to analyze that data as if those intervals between the units make sense. That would be an interval variable. An interval variable is something like temperature. So you have ordering, classification, but also the difference when going from 23 degrees Fahrenheit to 24 degrees Fahrenheit is the exact same difference, quantifiable difference, as going from 100 to 101 degrees Fahrenheit. So a difference, a shift of 1 unit on that scale is the exact same shift anywhere. And that's not the case for rankings, which is what ordinal variables generally are. And then the final group is an example that I've already given you, and that's age. A ratio variable differs from an interval variable in that the 0 has meaning. So when we measure things from patients where 0 indicates like a lack of whatever it is you're measuring, that's a ratio variable. That type of variable is the only kind of variable that we can actually describe between groups using ratios. That's why it's called a ratio variable. So things like risk. If your risk is 0, you have no risk. So that's why we tend to describe differences in risks in terms of ratios, because then you can talk about the fold change or the fold difference between groups. Age, those kinds of things. A lot of lab measures will be informative in a ratio comparison. The next aspect of this is understanding, and this is a direct function of the independent variable. So once you've identified your independent variable, you might also automatically answer this third bullet, which is how many samples are you comparing, how many groups are you comparing. So if your independent variable is like a treatment, and you have 2 different treatments that you're comparing, then you have 2 different samples. Your biggest question is whether or not your samples have any dependence. Are they completely different people, completely different patients, or are you repeatedly measuring the same group of individuals? Are there natural pairs, like if you're doing an observational study where you have selected a group of cases and you've matched them with controls? That's a paired or dependent sample situation. So the methods I'm going to talk today about are independent samples. When you get into repeated measurements and dependent samples, there are some simple methods, but for the most part, that becomes a little bit more complicated. And then finally, how big is your study? How many subjects were you able to recruit? How many subjects were you able to actually record outcomes on? Because that gets back to the idea of assumption checking. We never want to apply a statistical method unless we are absolutely certain that it's going to produce a valid result. in order to determine whether it's going to produce a valid result, we have to first kind of define, again, the scenario and make sure that the method is appropriate in the first place. And then we have to go and investigate the method itself and see how it was designed to be applied. Do the data need to be normally distributed? Or at least they need to look approximately normal? If I apply a t-test to data that don't meet the t-test's assumptions, I'm going to get a result. But that result is going to have zero meaning. It's going to produce a result that is not reflecting what you think it's reflecting. The p-value, the test statistic, the confidence interval that would result from that. So we have to be very careful about when we apply these. We just go look up the assumptions and then figure out how to check those assumptions with the data that you have in hand. One key to that, to the ability to do assumption checking is that you have to have enough data to do it. So if I have 10 subjects and I'm doing a t-test, a one-sample t-test, and I go to look for normality, can we really assess normality with just 10? Probably not, right? And so it's not that the t-test is inappropriate, it's just that we don't know if it's appropriate. We can't verify that we've met the assumptions. So that's why a lot of these, what we call parametric methods, require a little bit larger of a sample size. And it's not because they fail to work in smaller sample sizes, it's that we don't know if the scenario is appropriate because we don't have enough information to assess its appropriateness. So I'm going to blow through a couple of slides here just to show you that it can get overwhelming very quick. And this is kind of a highlight of the most commonly applied methods given some kind of a scenario that might come up in research. If I'm asking questions where the outcome, the dependent variable, is continuous, so something like age or oh my gosh, I can't even think of. Give me some continuous outcomes that you all work with. Weight loss. Very good, yeah. So those kinds of things where they're obviously continuous, and that is the outcome, we might want to compare that outcome in a single group to like some kind of historically established value to see if it's different, and that would be a one-sample test, where we really don't have an independent variable, right? We just have an outcome and we're looking to see if it's different from some value. That's just a one-sample t-test. If I do have an independent variable that measures, let's suppose, an exposure to something, they were either exposed or non-exposed, that independent variable is categorical. And so if we have like an exposed and unexposed group, or if we have a treatment and a control, that's just a two-sample t. We'll see that today. If we have a categorical outcome that reflects more than three or more groups, that t-test is no longer appropriate, and we'll see in a moment why. We have to apply something that will account for the fact that we have multiple groups and we're looking at differences in that outcome across those, and that's the analysis of variance framework, which basically does the same thing the t does. It just does it in a way that protects us from making a false positive finding. Now, still having our continuous dependent variable like weight loss, what if the predictor, in this case, is also continuous? So the simplest example of that would be correlation. If we're trying to correlate, like with a scatter plot, some kind of continuous x and continuous y, we'd see the scatter plot, and hopefully we see some kind of pattern that can be described by a line. So if that's the scenario, then we would have a single continuous independent variable with our single continuous dependent variable, and that would be simple linear regression. If we're interested in actually quantifying the relationship, if we're just wanting to see if there's a relationship, some kind of linear trend, correlation would be adequate. If we have, instead of a single continuous predictor, but maybe we have multiple predictors and they're all continuous, that's still linear regression. We just happen to call that multiple linear regression to reflect the fact that it has multiple predictors or multiple covariates. And finally, if we have a mix of categorical and continuous predictors, so for instance, weight loss as a function of type of diet, and age. Does that seem reasonable? Type of diet's categorical, a categorical predictor, and age is a continuous predictor. And if we want to use those together to simultaneously try to predict or describe weight loss behaviors in our study, then that would be multiple linear regression, but it also has a specific name which we refer to as analysis of covariance, depending on the type of question that we have. We can do these tests. In fact, I would say that with practice, most of you would be perfectly capable of doing this, even if you aren't a statistician, because they are relatively straightforward as long as you know and understand you need to check assumptions. So the assumptions for each of these tests really revolve around the behavior of the sample. So if your sample's large enough, then you can do a histogram of your outcome to see if it looks like that nice bell-shaped curve. You want to look for really unusually large and unusually small observations that could invalidate the test. You want to look for a lot of skewness, which could invalidate the test. Another assumption that you have to check when you're comparing groups is that the variation of the outcome in the groups being compared is about the same. You don't want to see massive amount of variation in the treatment group and very little variation in the control group, because that can throw off the results of your test as well. So again, these are what are called parametric approaches. The t-test, analysis of variance, correlation, linear regression, all require assumption checking. We make some assumptions about what the data will behave like in order for the results to be valid. There are some additional assumptions for correlation and regression that revolve around how the X and the Y in those models are related. They are designed, these are methods that are designed to capture linear relationships. And what I mean by that is if I have a continuous X and a continuous Y in a scatter plot, and I look at that cloud of data, a line should be what is going to adequately describe that relationship. Not some kind of curve or weird like sigmoidal shape. If it's not a line, then these are probably not appropriate. There are other methods that can actually describe those nonlinear relationships. And then, of course, I didn't mention it in here, but independence, right? That your subjects, knowing how one subject is going to respond doesn't inform how another subject is going to respond. So just working with random samples, not having the same patients in the groups being compared are all requirements of these tests. What happens often is that when we get done with our study's small and we can't tell, we don't have enough data to really tell whether we have achieved normality or it looks like normality is a reasonable assumption. We can't really tell about variation between the two groups, or we might have a large enough study to verify assumptions, but assumptions aren't met. When we plot the data, it's really skewed, or we have a lot of outliers that are valid data points that shouldn't be removed, or we have problems with variation in response. There are alternative strategies for analyzing that data. Instead of trying to twist the data and force it into some kind of shape that it doesn't really want to be in naturally, we can find another method that will be applicable to that kind of data. So these are what are called nonparametric methods. We also have something called semi-parametric methods, but again, beyond the scope of this class. Nonparametric methods have fewer restrictions on how they can be applied. They're more robust to all kinds of strange behaviors in the data. They're robust to outliers. Generally speaking, when we have continuous outcomes like weight loss, a non-parametric method will strip the actual value of weight loss from each patient and replace it with their ranked weight loss, either across the entire study or within groups, and then it will compare rankings between groups. So it's more like a median-based test. So again, comparisons, some alternatives to the t-test and to analysis of variance and to regression include the sign test, the median test, Mann-Whitney sometimes called Wilcoxon or Mann-Whitney-Wilcoxon or Wilcoxon-Mann-Whitney, because I think multiple people came up with it independently. Those are the counterparts to the 1 and 2 sample T. Kruskal-Wallis is a counterpart to the analysis of variance approach. Spearman correlation is an alternative to Pearson correlation. Spearman correlation is just correlating, again, the rankings of a continuous X and Y. And then there are regression models that account for things like skewness, a lot of outliers or a few outliers, differences in variation between groups. Weighted least squares regression will help with when you have a problem with your equal variance assumption in a regression scenario. And some of these others will account for problems with the actual distribution of the data, meaning if you have skewness or a lot of outlying observations, you could do something like a robust regression or a ridge regression and get a valid description of the relationship. Those can be done very easily in any package. I'm just giving you the RStudio functions that will perform these if you're interested in learning more about RStudio. Most people say, well, what are the consequences? Because we understand that anytime we make a decision to move beyond the parametric test to a more robust non-parametric test, well, why wouldn't we always do non-parametric tests if they're that good? Well, the reason why we wouldn't always do them is because there is a consequence, and that consequence is a reduction in power. It's a minimal reduction in most cases, but it is one nonetheless. So the benefit is they're robust. If your data does not meet the assumptions of the parametric method like the t-test, you shouldn't be doing the t-test. You should go and find a non-parametric test. And again, the loss of power has to do with the loss of information. When you strip away the outcome, the exact measurement of the outcome and replace it with a rank, you're losing information. So by definition, you're going to lose a little bit of power as well. But again, a good strategy is to default to a non-parametric or robust method because it's less likely to give you a false positive result and actually give you a valid result when you have problems with your data. This is what we would often talk about in like an intro to biostats class. You can see that it's not an easy thing to talk about statistics because there really are almost an infinite number of scenarios that could inform how you're going to analyze your data. I'll give these slides to you all so you can see kind of the hierarchy of methods and what's appropriate when. And again, just based on number of groups, whether you can verify assumptions, and whether you have independent or dependent samples. And this is just for comparing means, or averages, or what we call central tendency. There are other flowcharts if you're comparing, for instance, proportions, categorical outcomes, or if you're comparing variation. Now, let's get away from outcome measures like weight loss and look at outcome measures like a patient responds or they don't. So like a treatment failure or a treatment response, a categorical outcome. If you have that kind of outcome, and you have a variety of different predictors or independent variables, then there are different types of tests that you'll want to use. For instance, if you have a single group of patients and you're just measuring some kind of categorical outcome on them, then you're not comparing groups. You might be interested in seeing whether or not the fraction of patients responding is the same as it has been historically under some other treatment. So you have a single group and you're comparing it to a value. That's a one sample test, and that would be a chi-square test. In fact, the vast majority of these are going to be chi-square tests, just different formulations of the same thing. So the chi-square test in that case is called a goodness of fit test, but you could also do a binomial test, which is good when your categorical outcome is like a yes-no or a true-false, or a multinomial test, which is better when you have a categorical outcome that has more than two classes. So for instance, If you're a cancer researcher, very often we have a tumor response, which is classified as a complete response, a partial response, stable disease, or treatment failure. So that's a categorical outcome, but it has 4 levels now instead of just 2. That would be like a multinomial test. That'd be an example of that. Now suppose, and I actually had a question about this I think last week, now suppose you have that same categorical outcome, but you have a predictor. Let's say that predictor or that independent variable is some kind of treatment. And so you have treatment A versus treatment B. So you have a categorical X and a categorical Y. You often see that data presented in like a table, a contingency table, where you have the predictor defining the rows and the outcome defining the columns or vice versa. And that's a chi-square test as well. But what you're testing there, and I'll show you an example of this, is whether or not those 2 factors, let's say sex and response. Sex is male, female. Response is yes, they responded, no, they didn't. Are those 2 things associated? Is sex associated with the way patients respond to this therapy? And that would be a test of independence, again, using the chi-square statistic. And I'll show you the chi-square statistic, actually, how it works. It works very much like the T that we saw last week. And you might also be doing logistic regression in that case. And then if you have any measure of predictors and you want to do some kind of regression model, logistic regression is a fallback. It's very commonly applied. You're just trying to predict or explain how a yes-no response, you're trying to explain it as a function of some measures, some prognostic measures or treatments or exposures. There are other regression methods, again, kind of beyond the scope of this class, like Poisson regression, which is better for when your outcome is kind of a count, but it tends to fall in this categorical data. But that, again, you won't hear that word again from me because it is beyond the scope of this class. These tests are like the T and the ANOVA in that there are some assumptions. We don't have to check normality because we have a categorical dependent variable. What we have to be concerned with for these methods are how many patients fall into each of the classifications of both the independent variable if it's categorical, but also of the dependent variable if it's categorical. So for instance, if I'm interested in predicting response to some chemotherapy, looking at kind of classifying people who respond versus people who don't respond, well, what if everyone responds? So I have 100% of my data in one classification, and I have no data, no subjects in the other. Can I run that model? The answer is no. So we have to be concerned about the distribution of responses, if you will, between all of the potential responses that could occur from the categorical variable. That's why often you'll see when you talk about, and this is the case for survival analysis as well, when you talk about how powerful your study is, it's a function of the event rate. Because if you have very few events, it doesn't matter if you have thousands and thousands and thousands of patients. If 2 respond, there's nothing that you can do. Or if 2 have the event of interest, there's nothing that you can do. So it's more a function of how many fall into each of the bins as opposed to the overall size of the study. So checking the assumptions for these involves really kind of looking at sample sizes in those groups. These tests can all be done, again, in RStudio with some very simple application of functions by pulling in your data and indicating what is X and what is Y. Any questions about that? It's a lot of information to take in. Again, I'm going to share these slides with you so you can print them out or keep them somewhere. That way you can hopefully refer back to the possibilities of methods, or at least the common methods for these scenarios. Let's briefly, again, touch on hypothesis testing because everything we're going to do from here on out is related to hypothesis testing. So here on the left, I have a figure which represents the response, which is the y-axis, of subjects to 2 different therapies. On the left is treatment, on the right is placebo. The graphic here is what's called a box plot. There's actually 2 box and whisker plots. And the nice thing about these is that they help us very quickly visualize any differences in how patients are responding to different exposures or different treatments, where the response itself is continuous. So this middle line here is like the average response. And then these whiskers go up and down to the maximum or some function of the maximum and minimum response for patients on placebo and for patients on treatment. And sometimes you'll see single little observations outside of those boundaries, and those are usually flagged by the software as an outlying observation. So you might want to go and investigate what might make that individual different and make sure it's a valid endpoint or outcome. But the premise here is that from hypothesis testing, subjects who are treated differently tend to differ more than those subjects who are treated the same. So if 2 people receive the same treatment, then the only thing that should be describing their differences in outcomes are those things that are naturally inherent differences between the 2 subjects. If you have a nice homogeneous set of patients. If they receive different treatments, then their outcomes could vary because of that same natural variability, but also because of some impact of the treatment that they received. So the previous picture of a box plot is how we visualize differences in outcomes when the outcome is continuous. That could have been weight loss. This picture here is how we might visualize differences in response if the response is categorical. Notice here we have the predictor or the covariate or the independent variable of treatment representing the rows of this graphic, and the outcome is how patients either improved or did not. And so that's classified as according to none, some, or a marked improvement. And then the size of each of these bins represents the fraction of individuals in that particular treatment group who achieved that outcome. This graphic is produced with a single line in R, and I really like it for visualizing how categorical outcomes differ between groups. So you can see no improvement. The majority of placebo patients had no improvement. No improvement actually is reduced in the treated group, and we can see almost a majority, maybe a majority of patients in the treated group showed marked improvement. So if we classify as any improvement at all, then we would probably see a statistically significant increase in patients who are improving with the treatment as compared to placebo. Again, a quick review of notation and terminology because we will be using this over and over again. The independent variable is whatever the researcher is manipulating in the study. So it's the explanatory variable or the predictor variable in a clinical trial. In an epi-type study where you might just be observing things, it's the exposure status of the patient or maybe some potential risk factor for a disease. And then the outcome is the dependent variable, and that's the value that's expected to change as a function of the independent variable. We often call this the response or the outcome, but I'm going to try to refer to it in terms of independent and dependent variable. Let's revisit our LDL cholesterol example from last week, only now instead of comparing the average in a community to a value that an investigator thinks is reasonable, I'm actually going to compare 2 groups. Everything from here on out is going to be group comparisons as opposed to single group testing. So let's let these 2 values of mu sub A and mu sub B, again, remember we tend to represent the things we're trying to estimate with Greek letters just to kind of flag them as these things can't be directly observed. We need to get a sample in order to be able to estimate what their true value is. Let those 2 things reflect the unknown average LDL cholesterol levels for patients who are being treated with 2 competing drugs. We'll say drug A and drug B. If we want to see whether or not patients treated under these 2 conditions would have similar LDL cholesterol levels after the fact, then we would probably want to do a hypothesis test comparing their average LDL values. And that would be specified in the form of a null and an alternative hypothesis. Remember, these are competing theories for what we might see at the end of the study. The null hypothesis is generally the one that reflects our current state of knowledge, the current state of science, and that if we go into a study doing a comparison, then we're going to assume that there's no difference because no one's shown a difference before. So the null in this case is that they're equivalent. The average LDL cholesterol levels for patients treated with these two drugs will not differ. And that's indicated by a statement of equality. And it's usually the one that we want to invalidate because we want to move science forward. We want to find a difference, so hopefully we can target in on better therapies. That alternative hypothesis very often reflects an update to the way we think about how treatments work. And so in this case, it would be a difference in their LDL cholesterol levels. It's generally, again, a reflection of difference, a reflection of a treatment effect, and one that we wish to support. The way that hypothesis testing works is that we actually assume, I'm going to call it the current state of science, the current state of knowledge, scientific knowledge. We assume that that is what we're going to expect, that we're not going to find anything. And then we perform the study, we collect the data, and once we have observed outcomes for patients, we compare what we observe in the sample to what we would expect if the null hypothesis were true. In other words, whenever I get the average LDL cholesterol levels of these two groups of patients under drug A and drug B, I'm going to compare those values, and in particular the difference in the two values, the two averages, to what I would expect those differences to look like if the truth is that LDL cholesterol levels don't differ as a function of treatment. So again, the null hypothesis, if it's true, theoretically will yield similar sample means, similar LDL levels across the groups. If the alternative hypothesis is true, it will yield theoretically different sample means. Again, back to reiterate what we saw last week, there's always a chance that we could get a sample, even when it's collected in a way according to best practices, there's always a chance that it might not reflect the truth in the population simply because of sampling error or sampling variability. And so we quantify our chances of getting a sample like that with the type 1 error rate. The type 1 error rate, again, is the probability of a false positive finding. We also quantify another type of error that we can make, the probability of a false negative finding, with what we call the type 2 error. So if the truth is that there's no difference, there's a chance we could find a sample or get a sample that will tell us there's a difference, and that is the type 1 error rate. If the truth is that there is a difference, there's always a chance we could get a sample that would not reflect that. It would tell us that there is no difference, and that would be a type 2 error. So again, framing this in terms of that sampling distribution that describes the populations, the potential populations that could have generated our sample data. On the left-hand side, I have a potential population that could generate our data, and that is one that reflects a 10-unit difference. See the 10-unit difference here in average LDL cholesterol for groups A and B. So this kind of reflects the alternative hypothesis. If this is the population generating our data, I'm most likely going to see an average difference, a difference in the averages somewhere around minus 10. If, however, the null hypothesis is true, I'm most likely to get values that reflect no difference, which would be around 0. And again, just to remind you all, the height of this function over the different values of the difference in these two means, the height reflects the likelihood of observing that actual difference in a sample. So if it's really high, I'm most likely to get it. If it's really low, I'm not likely to get it. Not really likely to get a value out here of about 7 if the truth is that there's no difference. And so when we get our data, we have to basically compare it against these two just to see which one most likely generated it. So when we collect the information on LDL levels for these two treated groups, these two samples, we see an average LDL level of 141 in group A and 140 in group B. So the difference between those two is a unit of 1. And that appears to come from the null hypothesis. So if I actually were to crank through and do this test, I'm probably not going to reject the null. Suppose in a different study, in a different reality, I did the same study and I achieved a difference of 15. I'm sorry, 20, hold on. 35, yeah, 15. So a mean of 125 in treatment A, a mean of 140 in treatment B, so a 15-unit difference in favor of A, which falls down here. That does not look like it came from the null hypothesis. It looks like it came from the alternative, that there is some difference. In fact, it looks like a difference in favor of A. Those two scenarios, I don't really even need, I need to do a hypothesis test, but I think we already know what the outcome of the hypothesis test will be. One will say reject the null, one will say fail to reject the null. When hypothesis testing is really useful is when we get data like this, which is actually what we usually get. We don't get really super strong and huge differences. If I get a really big difference, I often want to know what I did wrong to see that difference, because usually things are not, science doesn't move in big leaps and bounds. We make baby steps. So this is often what we see. We see a 5-unit difference. Treatment A resulted in an LDL level of 135 on average. Treatment B resulted in an LDL level of 140. So that's a 5-unit difference in favor of A. So there are a couple of things that could cause me to see a 5-unit difference. It could be that I have a flawed study. And for whatever reason, some of those flaws result in bias or error that give me this result. Hopefully I've done a good job of designing the study, and that's not the case. So if I'm confident in my study design, then I need to go and then ask myself a second question. Is my study big enough to ensure that this is not a function of sampling error? Because remember, sampling error is really big when we have small studies. So small studies are more likely to generate estimates or conclusions that are not reflective of the truth, either type 1 or type 2 errors. They're much more likely, just because small studies are more likely to generate samples that are unusual, just because you don't have a lot of the population examined in your sample. So I'm going to perform hypothesis testing, and I'm going to generate a test statistic and a p-value that will quantify how big this difference is and what is my risk of this being a function simply of sampling error. And I do that using, again, in hypothesis testing, a test statistic. The one we saw last week was the T, where we saw the signal to noise ratio. The T is useful when we're hypothesizing about means. The chi-square, I told you I would show you that statistic. Notice it looks a little bit like the T. It's still a signal-to-noise ratio, and that's useful when we're hypothesizing about count data or proportions. So proportions happen when I'm interested in comparing, for instance, the number of patients who respond under treatment A to the number of patients who respond under treatment B. Can you all hold one just a moment? Give me just a second. We are going to have to pause and move to lead. Apparently we're in lead today instead of in here. So I apologize. If you all want to, does everyone know where lead auditorium is? We'll walk over there. For those of you who are online, we'll be back in about 7 minutes. Thank you.